Let's continue with moment of inertia and angular rotational motion. So the key point is, in linear motion, mass is proportional to inertia, and in rotational or angular motion, it is the distribution of mass that is key. So the question is the moment of inertia constant in the human body? And so I need to remind you that we can rotate about 3 axes: our longitudinal axis, our anterior-posterior axis, and our medial-lateral axis. So let's look at those. The medial-lateral impales us side to side, and so we do front flips, if you will, and so that's a pretty big moment of inertia up from the center of rotation up to our head, center of rotation down to our feet. As compared to the longitudinal axis, which is kind of a pole kind of put in the top of our head, and we rotate like a ballerina, and that has a much smaller moment of inertia. The distribution of mass, let me see if I can get my pointer. The distribution of mass is much smaller from the center of rotation than it is from the medial lateral axis. Okay, and again, AP, we also have a large moment of inertia. So the question is, no, the moment of inertia is not constant in the human body. It depends on the axis of rotation about which that you are rotating. So here's a sample. I'll give you a few seconds to read, and then we'll go through these. So let's take one at a time. So we have Anna is standing on her left foot. Her right foot is abducted at 20 degrees from the hip. Her left arm is abducted 60 degrees at the glenohumeral joint. All right. Then we have Brian, who is standing on his right foot. His left knee is flexed at 90 degrees at the ankle. At the knee joint. Each arm is slightly abducted 15 degrees and flexed 90 degrees at the elbow. Then we have Catherine standing on her right foot. Her left leg is abducted at the hip 60 degrees, and each arm is abducted 100 degrees at the glenohumeral joint. And then we finally have Mike. His left arm is flexed 180 degrees. His right arm is slightly adducted past anatomical position, and then both feet are on the ground. So if we looked at the moment of inertia about the longitudinal axis, who has the greatest moment of inertia? You're assuming their masses are the same. And so now you're looking at who has the biggest radius from this center of rotation. And the answer that you should come up with is that Catherine has the greatest moment of inertia and Mike has the smallest moment of inertia. Now I warn you, I could ask the question, what's the moment of inertia relative to the AP axis, right? And then you'd have to deal with distribution of moment from this AP axis or the ML axis. But for now, this example just shows us about the longitudinal. Catherine has the greatest moment of inertia, and Mike has the smallest moment of inertia. Oh, I have it here.